Well, good morning, everybody. Welcome to day 2 of the Virginia Concrete Conference. It's a beautiful day here in South Carolina where I'm sitting, and I hope it's beautiful wherever you are too. Uh, for those of you that might not have been here yesterday, just a brief bit of housekeeping. The speakers today have pre-recorded their presentations, and then they will be online uh, with us live after the presentation to discuss it and answer any questions that might have come up. In the meantime, during the presentation, if you have any questions, you'll notice there is a YouTube chat next to the live stream. And so you can put your questions in the live stream, and we will be watching that during the presentation and either trying to answer them on the chat or in the discussion at the end. So with that, I guess settle in, and we'll get started with our first presentation today, which is the construction of I-95 southbound over the Rappahannock River. And we have 3 speakers on this, so I'm going to introduce all 3 going in here. The first one is Robert Ridgell. He's a professional engineer with the Virginia DOT's Fredericksburg District. He's the district mega projects engineer for the Fredericksburg District of the Virginia Department of Transportation and the project manager for the I-95 Rappahannock River crossing projects. Robert is a 2008 graduate of Virginia Tech with a bachelor's degree in civil engineering. Our second of 3 speakers today is Jerry Whitlock, and he's with Wagman. Jerry Whitlock is a design build coordinator for Wagman and for the I-95 southbound Rappahannock River crossing project. Jerry is a 2002 graduate of the Virginia Military Institute with a bachelor's degree in civil engineering and a 2003 graduate of West Virginia University with a master's degree in civil engineering. Mr. Whitlock has 20 years of combined military and civilian construction experience and is currently a commander in the U.S. Navy Civil Engineer Corps. And our third speaker is Trip Fopp with Johnson, Merriman, and Thompson, or JMT. And he serves as the lead structural engineer for the I-95 Rappahannock River crossing projects, is responsible for the design of the 2 new bridges across the Rappahannock River and 4 new bridges across Route 17. Mr. Fopp received a BS degree in civil engineering and a master, or an MS degree rather, in civil engineering with an emphasis in structures from Virginia Tech, and also received an MBA degree from Virginia Commonwealth University. So without any more ado, we'll start that presentation.
Hello and welcome to the presentation at the 2021 Annual Virginia Concrete Conference for the I-95 Rappahannock River Crossing Project. I'm Robert Ridgell, the Virginia Department of Transportation Project Manager for the project. I'm joined today by Jerry Whitlock, the Design Build Coordinator for the I-95 Southbound Project and the Entrusted Engineer for the I-95 Northbound River Crossing Project, and Trip Fopp, the Structural Engineer from JMT for the projects. So for those who have not been up and down the I-95 corridor recently, which is kind of hard to avoid in the Fredericksburg area, you'll notice our project runs from about a mile south of the Route 3 interchange at exit 130 to about a mile north of the Truslow Bridge project, which then segues into the Fredericksburg Express Lanes project. So if you've been in the area, you've seen that Fredericksburg is pretty much a construction zone from Route 3 all the way to the Prince William County line. Today, we're going to talk a little bit and focus in on some of the signature elements of the I-95 Rappahannock River crossing projects, namely the major bridge crossings over the Rappahannock River Gorge in the Fredericksburg area, which has always been a bit of a choke point for I-95. So some fast facts about the project. The project will reduce congestion on I-95 by essentially doubling the capacity both southbound and northbound and providing separate through and local lanes between the Route 3 and Route 17 interchanges. This is going to provide necessary storage capacity for local traffic that might be backing up on other arterial roads and allow through travelers to avoid that Fredericksburg bottleneck that we've had for years. Additionally, the project replaces the structurally deficient southbound and northbound I-95 bridges over Route 17 that also had an overheight restriction on the Route 17 corridor. This is a big component of the projects. 3 of the bridges being replaced under the southbound project, and the last and final northbound CD lanes bridge being replaced under the northbound Rappahannock River Crossing project. The respective contract values, $102 million on the southbound project and $107 million on the northbound project. Here you can see a slide that shows our overall construction schedule. It's been very fast-paced and aggressive to build these projects in the amount of time we have. We're planning to deliver the southbound project by spring of 2022, late spring into summer. And then we will be delivering the northbound project by spring of 2024, wrapping up and being the keynote for the Improved 95 program associated with the Fast Lane grants and the Atlantic Gateway. Additionally to that, we also are going to have some important elements that are going to come along, some milestones, including completing the Route 17 interchange and completing the signature bridges over the Rappahannock River. So by fall of this year, you should see the superstructure in place on the southbound I-95 Rappahannock Bridge. And then right now, we're already beginning substructure construction by flipping our causeway and beginning some of the other work to work on the northbound bridge. And here you can see our final roadway configuration. You'll notice that we're building essentially 6 new lanes, 3 in each direction, in the median of existing 995 between 130 and 133. This presents some very unique constructability challenges that really come home when we get down to the Rappahannock River and have to build these 2 bridges to carry those lanes in the median. And here you can see the existing bridges that were built with the original I-95 and then subsequently widened that are carrying the existing GP lane traffic. These will become the future CD lane bridges when the through lanes open in the median.
The existing southbound bridge is a 10-span structure, about 1,298 feet long. The northbound bridge is 8 spans and about 1,083 feet long. The concrete substructure units are reinforced concrete, and the superstructure are simple span painted structural steel plate girders. When we started looking at the proposed bridges within the median, first thing that we did was set the interior span lengths, keeping 3 things in mind. 1, avoiding the historic resources on the south side, the Rappahannock Canal and lock system, maintaining the channel in the river on the north side, and minimizing the number of piers. So what we decided to do was to set our new Pier 1 right in line with existing southbound Pier 1, then skip every other pier, resulting in 270-foot span lengths. For the total bridge, a 5-span structure, 1,200 feet long. As Robert mentioned, the transverse section accommodates 3 new 12-foot travel lanes, 12-foot shoulders. We're using 42-inch high concrete parapets, meeting the test level 5 criteria. And based on the span lengths, continuous structural steel plate girders were the chosen superstructure alternate, and we maximized that girder spacing out at 11 foot 4 inches. During preliminary design, we evaluated hybrid girders using 70 KSI steel in the flanges, and we also evaluated haunched girders. But working with Wagman and the fabricator, neither of those options were as economical as what we ended up with, a conventional grade 50 weathering steel system.
So what you see here, access in the corridor is very tight. So our team spent a significant amount of resources during the proposal stage to develop a causeway layout that provided necessary access to build the tall concrete substructure and to erect the superstructure steel. The picture on the left is our proposed causeway layout, highlighting our pedestrian and river user accommodations. And the picture on the right is a photo of Bridge 2 to Causeway looking downstream. One of the big hurdles we had to overcome was the development of a proprietary temporary bridge system that we could rapidly remove and reset. It could handle the loads of a 400-ton crane and had a low enough profile to allow the maximum amount of water underneath of our 50-foot openings. A key here is we had to remove the bridge number 3 during the peak recreational season for the river. As part of our causeway development, we also analyzed the previous 10 years of river elevation data to determine causeway height. And we set our causeway height where the data shown that it would have only been overtopped 8 times in the last 10 years. But as you can see here, Mother Nature had other plans for the year 2020. This series of photos was taken 23 to 28 December of 2020. And you can see our causeway just got wiped out. And this was the 5th time that our causeway had gotten overtopped just in 2020 alone, far surpassing the last 10 years of data. You also see here we've got a graphic of our time of year restrictions for when we can work in the river and when we could not. And in the graphic at the bottom is our last 10 years worth of data that we had put together for a proposal showing how we determined our causeway height. So one of the key aspects of this job was working in and around the pedestrians and river users. So we worked with several groups, including the Friends of the Rappahannock and the Fredericksburg Trail Alliance, to maintain access to the river and access to the trails on either side of the river during construction. You know, like I mentioned before, Bridge 3 was taken out of place during peak river season so that the users had free access. And when Bridge 3 was in place, we had installed temporary portages for river users to utilize to avoid the dangers of trying to go under that bridge. A key here as well is you'll see the gentleman in the center is a regular runner on the trail down by the river. And every Friday during our initial construction season, he would run about 2 miles carrying a couple boxes of donuts for the crew down there, just as a thank you for the neat work site that they kept and their maintenance of access for the trail users during construction.
Yeah. And Jerry, just to emphasize, the department's stake in having happy stakeholders and a happy community with the project is tremendous and has enabled us to do all kinds of great projects and really accelerated and helped us gain the credibility needed to even facilitate the Chatham Bridge project further downstream at the city of Fredericksburg. So it can't be overstated how important these relationships with our public stakeholders are, particularly on a project with this much construction constraint and elements that's going on in a critical recreational area for the Fredericksburg community, whether that's the Fredericksburg Trail Alliance or the Friends of the Rappahannock.
As we look at the elements of the bridge, the abutment A on the south end is a Virginia alternate abutment. It's founded on spread footing on rock. And as you can see, the abutment is located adjacent to the existing southbound abutment. So in that picture on the left, you can see that the construction did require temporary supportive excavation to protect I-95 and a current progress photo of that abutment on the right. Abutment B on the north side is also a Virginia alternate abutment, but it's founded on steel H-piles. Rock in that area did vary fairly significantly, and using steel H-piles in pre-drilled holes was the best solution there. That abutment is located close to the last pier on the northern end of the existing southbound bridge. And because of that, that abutment is a little bit higher than abutment A, and MSE walls for the abutment and wing walls were a very economical solution at that location. The piers have hammerhead caps and columns with rounded ends. The pier height from the top of the cap to the bottom of the footing for the river piers is approximately 92 feet, or a little over 9 stories. All piers are founded on rock, either granite or gneiss. The river piers 2 and 3 required cofferdams for foundation construction, and land piers 1 and 4 required temporary supportive excavation. The photo at the left shows the Pier 4 supportive excavation and the condition of the rock foundation.
You could say that rock looks real nice, Tripp.
Thank you. One challenge during project pursuit was to determine how we could get into the river to obtain the borings for those river piers, and to do it within time of year restrictions established by environmental agencies, getting an environmental permit to do that work, and also to do that within the scope validation period identified in the RFP documents. We did have existing information from the as-built plans and limited borings that VDOT provided us. So what we did was develop a composite section at each pier, showing the existing and proposed piers, including where the bottom of the footings were, and also where that anticipated rock profile is located, as we show in red in this figure, and based on the existing information that we had. So once we did this, we felt very confident where anticipated rock would be located for these river piers. And as a team, JMT and Wagman, we decided to waive the scope validation process at the river piers and assume all of the risk associated with changed conditions due to foundations. We discussed this with VDOT at our proprietary meeting, and we provided a write-up of this process in our technical proposal.
And so here you can see some pictures to emphasize the importance of this overall waiver of the scope validation and the potential gains to the project delivery schedule and potential reductions in the price proposal from not having to do these preliminary river borings. Here in these pictures, you can see Fredericksburg District's attempts to go in and do our borings for the GDR going into this. So with environmental permitting being what it was, building a preliminary causeway was right out. That wasn't going to be an option to be able to get the job on the street in time. So Fredericksburg District Construction, led by Mike Coffey, as well as our district materials in coordination with central office materials, came up with this idea to use a marsh buggy, which is this tracked drilling platform that you can see in front of you. Now, I was down there when they assembled this thing, and I have to be honest, the geotech engineer in me, which is my background, was nerding out when I saw this thing being constructed and going out there to basically cowboy a drill rig out into the Rappahannock River. But as you might notice in that center picture, you'll notice that it has steel and aluminum constructed tracks. This thing is designed for moving around in a marsh, like the Florida Everglades or somewhere in Louisiana, not necessarily a hard rock bottom with significant rock outcrops and boulders abound. And I can tell you on the very first day we watched this thing go out there, I watched this thing launch up a boulder at like 30 degrees, get up on the top, teeter for a second, and then come back down the other side. It was impressive to watch, but if you go all the way over to this third picture on the right-hand side, you can actually see where that left-hand track actually broke, disabling the unit and leaving it stuck in the river at one point. At this point, we had to go have an emergency contract to bring in a local contractor with off-road excavation equipment to bring that machine back out of the river. So avoiding these preliminary borings, avoiding the time associated with building a preliminary causeway to get out there, or using other unconventional methods that present an environmental risk, were actually a critical component of the fast-paced delivery of this job.
So after notice to proceed and winning the project and obtaining that notice to proceed, the Wagman JMT team, we obtained the environmental permit, we constructed that temporary causeway, and we went ahead and performed that geotechnical investigation. Now, while this was going on, we were doing final design for that pier based on what we had originally assumed. So this is going hand in hand to expedite this construction process. But we actually got out there and we performed that work outside of the time of year restrictions and also after the scope validation period. The results of our study here and the investigations, it did confirm our original assumptions and allowed us to continue moving forward with the project.
So the size of our substructure elements triggered mass concrete plan for this project. And VDOT defines mass concrete as anything over 5 foot in lateral dimension. So the entirety of our pier substructure required mass concrete. So what we did as a team, we went out and hired an expert in mass concrete to develop our mix design and our mass concrete monitoring plan. On the left, you'll see one of our maturity sensors on the left top, and in the left bottom, you'll see several of them installed prior to a pour. We also have a representative temperature graph here that shows our concrete mix matured between 24 and 50 hours based on where it was located within the pour itself. The center and right photos, you'll see how we protected the concrete to keep the temperatures consistent and also to protect from the winter because we had to pour through the winter to keep our extremely aggressive project schedule. So here you see the original RFP layout of the northbound and southbound bridges relative to the existing bridges. And the bottom, you see what the proposed layout that we ended up with. After going through several iterations, looking at different aspects, trying to come up with the most economical layout for girder erection is what it came down to, while still providing VDOT with their requirements for future maintenance and future inspection.
During our proprietary meetings with VDOT, as Jerry said, we did do a lot of legwork to determine that it was feasible to inspect these bridges down the road. We found a local provider of that inspection equipment, and the snooper that we identified had no challenges reaching under that bridge, both for the southbound and the northbound. And one thing that it did do by that type of equipment, those inspections will be occurring from the right-hand shoulder there, so provided a much safer inspection procedure in the future.
So this is an example of some of the graphics we put together during the proposal stage to show proof of concept for our structural steel erection and how our layout was more economical than the original layout proposed in the RFP. The original layout of the RFP would have required the use of shoring towers in order to erect this steel using cranes or some sort of girder launching scheme, which are substantially more expensive than the use of cranes to erect the steel. You also see in this photo how our northbound causeway is very similar to our original southbound causeway, which is what's in yellow. And that was a key of our proposal as well, in that our causeway size got slightly smaller for the northbound, keeping everything within our already existing permits, requiring very minor modifications to complete the permitting process through the agencies for our causeway. This is a plan view that we developed for VDOT as proof of concept for our bridge layout. Show that we can pick the majority of the steel either from the new southbound bridge or down below from the causeway, and that we didn't have to utilize the existing northbound bridge or existing southbound bridge for our steel erection.
High steel erectors perform the erection for Wagman, and as part of their process, they had to develop a detailed erection plan, including calculations for each and every girder pick. They use 2 cranes during erection. In the left-hand picture, the yellow crane is a 450-ton crane, and the white crane below in that picture is a 385-ton crane. When they set the end spans, 1 crane was located behind the abutment, and 1 crane was located down on the causeway. When they set interior spans, both cranes were moved down to the causeway. Picture on the right just shows what a constrained work area we had as we did this girder erection. The first girder line is approximately 10 feet away from the southbound bridge, so really required a great plan and a safe plan to put those girders into place. So we've done the planning as Jerry described, the design process both from the engineer and the erector. We've built the access causeway, and we've got our cranes on site to help us do the erection. But when it comes down to it, it's the individual iron workers who perform the erection. Looking at the left-hand photo, you'll see the iron workers in their cage waiting on the girder as it comes from the right from the crane. And then that iron worker in the middle picture grabbing that piece of girder with the spud wrench, and that's what really puts it all together. And then on the right, they've pulled it home and they've started to put the splice bolts in to complete that segment erection there. The girder erection progressed about 1 span each week, but a couple things occurred during erection. One, we did revise our erection plan to incorporate lessons learned and to make sure we had the most safest operation as we did that work. And then, as Jerry mentioned, the causeway did wash out multiple times during erection. But with persistence from Wagman, High Steel, and including the department, it resulted in a successful girder erection. And you can see the last girder going in place. It's held up by that yellow crane on the right-hand side. On this project, concrete is a proven solution. We're showing the volumes for the various elements, and the total concrete used on the project is over 13,000 cubic yards.
So if you'd like to reach out or find more information about the project, you can reach out to any of the contact information you have here, whether it be me, Jerry, Tripp. We're available. We also, it's not on this slide, but we do have a Facebook group for VDOT Fredericksburg, the Improved 95 website, and a litany of other social media accounts that you can reach out and stay in touch and learn more about the project. And with that, we are more than happy to hang around and take any more questions for our allotted conference mandated time. I just joke. We'll stay as long as you need us, and we're happy to answer your questions.
All right. Well, great. Thank you so much for that presentation, guys. That was an excellent presentation, and it certainly got us a lot of discussion about your geology joke there. And so I guess if y'all would, the speakers would unmute. Do you have any other last points you want to make? We have about 5 minutes before we get to our next presentation.
Yeah, this is Tripp, and I'll respond a little bit more to Junyi's question about the issues with the Virginia abutment. There were no real issues with the design of the abutment. It went pretty smoothly following VDOT standard detailing practices. Really, the challenges related to the varying geology at each abutment. So we had really good rock, and setting on a spread footing was very, very reasonable. At abutment B, the geology was a little bit different with the rock dipping away, kind of transverse to the bridge. So short piles on one end, longer ones at the other. So just making sure we had that abutment footing set where we wanted to have it was a challenge. And then the other challenge was, the construction of the southbound bridge occurred first, and we were not sure if we would win the northbound project, so it was detailed as a standalone abutment. But when we won northbound, then we quickly had to change gears and figure out how to retrofit the southbound abutment so that the northbound abutment could tie right into it. So there are a little bit of challenges working the details out there. We did think about it during the southbound design, but putting it in place was a little bit of challenge. But everything seemed to work out pretty good.
And to that end, I think that the reason they have to be tied together, Trip, was because, and as we're still kind of dealing with, there are some significant drainage concerns there regarding maintenance access for the actual trough in the Virginia abutment, because this bridge is large enough, the trough is big enough to facilitate like critters and other things like that getting in there. So we've had a lot of discussions about how to prevent that and keep it accessible for maintenance purposes and keeping that trough clear. And then on top of that, a lot of detailing and a lot of coordination between Tripp and his roadway peers to work out the drainage scenario around that abutment, because it's on top of that, we're sitting there on that hard slope of the Rappahannock River Gorge, and so you have very limited paths for that drainage. You're not looking at sheet flows and stuff over there for sure.
Right. And Robert, one more just to help Junyi out, and I'm certainly willing to talk with him offline, but looking at alternate ways to discharge the water that's in the trough. I think the design aids show it discharging out of the end, but we did evaluate other means to get rid of the water that was in that trough. And like Robert said, on a real wide bridge, sometimes that can be a little tricky.
I see there's another question up here that's asking why a continuous superstructure was not a better option. Any of y'all able to perhaps address that?
Maybe I'll ask Samsor to clarify the question. Our bridge, the northbound and the southbound that we are constructing, they are continuous superstructures. The span links kind of forced us to go to the structural steel option, and we did use continuous structural steel plate girders for both of the river bridges on I-95. So I hope that answers Samsor's question.
Okay, well, great. Again, gentlemen, thank you. I know y'all will probably be hanging around. If there's anything else that we can address or y'all can address in the chat, we'd certainly encourage you to do so. And a couple of things I think I failed to mention. One, I'm not sure if I said who I am. I'm Andy Johnson. I'm the pavement design engineer for the Southeast Cement Promotion Association, and have prior to that was I'm a retiree from the South Carolina DOT, so I've been around for a long time. And during the presentation, there were a number of comments that the presentation was blurry, and we apologize for that. A little inside baseball here. What we are doing is actually a WebEx that is then being transferred to the YouTube stream. And so unfortunately, we're suffering some loss of resolution in that transfer, but WebEx had some capacity constraints, and the number of people we had, we wanted to make sure it worked for everybody. However, these presentations will be available online in a few days after the conference is over. And so if there's anything you'd like to see, you can see these presentations in their original resolution, which will be a lot sharper. So we apologize for this. This is our first and hopefully our very last virtual concrete conference, and we'll be aiming to be back live next year. So again, please bear with us, but you can eventually see these things in their original high definition glory. All right, well, on that note, we're going to move to our next presentation, and that's going to be state-of-the-art design and construction provisions for practice. And our presenter today is Mike Kulmo with CHA Consulting, and Mike is a structural engineer with 37 years experience in bridge and highway design. He has extensive experience in the design of steel, concrete, and pre-stressed precast concrete bridges, and has special expertise in the field of accelerated bridge construction technologies. He holds a bachelor's degree in civil engineering and a master's degree in structural engineering, both from the University of Connecticut, and is a licensed professional engineer in 8 states. So with that, we'll roll his presentation and be back live with you in a few minutes.
It's my pleasure to be here today to talk about accelerated bridge construction, and specifically the state of practice for design and construction provisions in the U.S. The current state of practice for ABC is widespread in the U.S., and virtually every state has been using ABC or has used ABC, and many states have ABC programs. Until recently, design and construction specifications were an issue. There were no national specs, but now we do have a national spec. The 2018 AASHTO guide specifications for ABC are primarily what I'll be discussing today. Also, AASHTO has assigned Technical Committee T4, which is the construction committee, to be the home for ABC at AASHTO. Industry has stepped up. Many industries, the steel industry and the precast industry, have stepped up. PCI National, and I'll be speaking quite a bit today about the PCI Northeast Bridge Tech Committee, which is a committee comprised primarily of DOTs, 7 DOTs in the Northeast, plus producers and some consultants. I've been a member of this committee for 30 years, and we've published many ABC guidelines that are available for free download. Here's a listing of some of those guidelines, both national and the Northeast documents. The Northeast documents can be downloaded at www.pcine.org. As you can see, there's a whole bunch of guidelines here that are all applicable to ABC, and they're very useful documents. Federal Highway also has 3 very good documents on their site. You can search FHWA ABC, and you'll find their site where you can download these documents for free. The first bulleted item here is a general ABC, basically ABC cover to cover manual. The second document is really a design manual, engineering, design, and fabrication and erection of PBES. And the last one is construction and contracting of ABC, which is useful for managing a construction project. Other great references that are available, NCFRP Project 1298 developed 2 guidelines with respect to ABC. The first is a guideline on tolerances, where we specify, it gives recommendations for specifications for tolerances for elements, tolerances for erection of elements, and most importantly, tolerances for joints between elements, which is used to accommodate tolerances. If you want a job to come out correctly, this is an important guide to follow. Also, guidelines for dynamic effects of bridge systems. We have found that moving bridges and SPMTs causes significant dynamic effects On the false work, the SPMTs, and even the bridge. So research was done to develop design guidelines for dynamics. Both of these documents are referenced in the guide specifications, so they're worth downloading. They are available for free. You can search NCHRP Project 1298 website. You can download the documents. You can also download the report that led to those documents. If you want more information, you could actually go to FIU ABC UTC website, and there are webinar archives for 2 presentations that were given on both of these documents. Again, they are all free for download. So let's dive into the guide spec and see what it contains. The first 5 sections of the guide spec are design provisions. I'll talk a little bit of more detail in the next few slides. The last 7 sections are construction specifications. Due to the brevity of today's presentation, I can't get too deep into those, but they are available and they are full AASHTO format construction specifications for all these items. Let's dive a little deeper into the first 5 sections. Section 1 is an introductory section. It includes definitions, and you might think that's boring, but it's important that we have common terminology that we use. For instance, the gap between elements, we refer to those as joints, closure joints. Sometimes people refer to them as closure pours because we're pouring concrete or UHPC into the joint, but AASHTO has made a decision to use the term closure joints. That's just an example of some of the definitions that we have. Section 2 has general design provisions outlining responsibilities for the contractor and the engineer. Shipping and handling provisions are listed, which is important to know, as is commonly misunderstood, that shipping and handling lifting calculations are the responsibility of the fabricator, not the engineer. This is contractor means and methods. But we do have provisions that you can specify for the contractor or the fabricator to follow. We have load combinations for design of prefabricated elements, but also load combinations have been developed for SPMT and lateral slide bridge moves. This includes dynamics that I mentioned before. Section 3 is the major design section in the document. The key thing is the majority of the specifications in the document are based on emulation. And emulation is a term that means we are emulating cast-in-place construction with precast. The key thing about emulative design is that if you use emulation, your design of the structure as a whole can be based on cast-in-place construction. So analyzing a pier, analyzing abutments, walls, all that can be done using standard AASHTO provisions. There are significant seismic provisions in this section. Now, there's also several provisions that are not covered in the AASHTO LRFD bridge design specs. For example, the bridge design specs include provisions for development of hooked bars, but there are no provisions for lapping of hooked bars, which is a common ABC detail. The guide spec contains those provisions. UHPC is very popular. We have provisions for design and construction specs for that. Mechanical connectors, the current AASHTO bridge design specification has mechanical connectors for reinforcing. The basis of that is the connector needs to develop 125% of the specified yield strength of the bar. ACI has a second level, type 2 mechanical connectors, which can develop 100% of the specified tensile strength, which is a higher level. For a grade 60 bar, that's 150% of FY. So we do recommend using mechanical connectors type 2 for critical connections. The guide spec includes pocket connections and socket connections that are not in the AASHTO LRFD bridge design specs, as well as link slabs. We'll talk a little more about that later. Section 4 includes detailing requirements, and this is where we get into requirements for layout and tolerances, how to specify tolerances, how to specify layout and precast elements. And again, this is a reference to the NCHRP Project 1298 guidelines that I mentioned before. Section 5 includes recommendations for durable structures, ABC. In ABC, we do not want to detail a bridge that's fast to construct but sacrifice quality. Every specification in the guide specification was measured for durability. If a detail that had been used was not considered durable, it did not make it into the guide specs. We want to make sure we maintain durability. In that section 5, we include provisions for jointless bridges using link slabs or integral or semi-integral abutments. That's an example. Let's go look at some of the highlights of the specification, things that are important to know. When it comes to SPMT systems and lateral slides, we have provisions defining responsibilities for who is responsible for what. These two types of construction require a significant amount of work by the contractor as far as engineering, involving temporary shoring, jacking systems, and the SPMT design itself. All of that is contractor means and methods, but we do give provisions for the engineer to do preliminary calculations for things like SPMT layouts. We also have responsibilities for prefabricated elements. As I said before, lifting and handling is the responsibility of the contractor. However, the design of the element is the responsibility of the load combinations are included in Guide Spec Section 2. And this is just simply stating if you're using an emulative design process, you just essentially design the structure according to the AASHTO LRFD bridge design specifications. As I mentioned, we have provisions for shipping and handling. We recommend that the engineers specify these provisions for the contractor to follow. And these are based on work done at PCI. Essentially, we use dynamic load modifiers to increase the dead load to account for dynamics. This table shows the modifiers that are used in the PCI documents. Essentially, things that engineers typically don't think about is there's significant force effects when you remove a precast piece from the form due to form suction and adherence of the piece to the form. This is often the controlling load case when checking an element for lifting and handling, because at this time, typically the concrete strength is not at its full strength, it's at its initial strength. Again, this is the realm of the contractor's means and methods, but we want the engineers to know the correct process to follow for this. The PCI MNL 120 document is listed on the right in the commentary. That document does include examples for how to calculate lifting and handling calculations. We recommend that designers specify that document as a requirement. Section 3 is the largest section in the guide spec at 85 pages. It includes all the design provisions. It includes seismic provisions, which we're not going to cover in much detail today. We just don't have time to cover all the provisions, but we'll breeze over a few of them just to give you a flavor for what's in the spec. So as far as design of PBES, again, Section 3 covers the design, and this is where we say that you need to design according to the AASHTO LRFD bridge design specifications and use emulative design approach. As far as connections go, they're very important in prefabricated and precast elements. The most common connections are covered, the ones that we see across the country. The term that we use for these closure joints are cast-in-place closure joints using lapped bar reinforcement. This covers, the provisions cover straight bars, lapped-headed bars, lapped hooked bars, and lap bars with UHPC. These are all covered in the spec. We cover mechanical connectors. I mentioned that before, the Type 1 and Type 2 connectors. Bars inserted in grouted post-tensioning ducts, that's a version of a mechanical connector. We also cover pocket connections and socket connections. There's some confusion in the market about what a pocket connection is and what a socket is. And the best way to describe it is the next slide shows nice graphics. A pocket connection shown on the left is a connection where reinforcing from one element is passed into a void in the second element that is filled with a material. Usually it's concrete. So that's a pocket connection. A socket connection is where a portion of an element is inserted within the adjacent element. And there's two details shown on the right. The top one is a column that is set into a footing that's cast in place. That is a socket connection. And the bottom detail is a column inserted into a void in, say, a pier cap, which is also a socket connection. So the best way to remember what a socket connection is think of a light bulb that you screw into a light socket. That's the best analogy that I have to a socket connection. So if you understand that, then everything else is a pocket connection. Let's show some of my favorite pocket connections. This is a integral abutment detail where we use corrugated metal pipes that are cast into precast pieces, and they're set over piles, and the void is then filled with concrete to complete the connection. Very simple detail, very simple connection, easy to execute in the field. The key thing is, what is the resistance of that pile for punching through that void? And so we've developed an equation for the punching shear based on AASHTO provisions for interface shear. Section 3 covers grouted couplers. I mentioned this before. The grouted couplers essentially are a mechanical device made of cast steel that transfers force from one bar to the next. You see in the diagram on the right, the couplers can be located at the base of a column. They can be located inverted at the top of the footing. They also can be located inside the cap, pre-cap as well. You can connect walls, piers, anything with these couplers. The photo in the center shows a pier cap being installed in Utah. And you can see the projecting bars from the column, and you can see the couplers that are cast into the cap. The way we transfer force to these couplers is the bar force, the lower bar is transferred via the grout that's inside the coupler, and that's put in after the connection is made. It transfers the force from the bar to the coupler, then the force is transferred from the coupler through the grout to the upper bar, completing the connection. Some people are uncomfortable with these connectors. They're worried about they're going to function. the reality is they are basically built on the same concept as the lap splice in concrete, where force transfers from one bar to the next via the concrete around the bars. So if you can trust a lap splice to function, I think you can also trust these couplers to function as well. Another detail that came out of the PCI Northeast group was really one of my favorite details, where we try to simplify the construction of, say, an abutment by using standard wall panels for the lower portion of the abutment. We recommend using corrugated pipe voids in that piece to do two things. One is to reduce the weight of the piece, and two is to use it for connections. That void is filled with concrete in the field. But the really key to this detail is having one complex piece. It may be two pieces, but having a complex piece on top of the abutment that has things like the steps for beam seats, and have one complex piece and a whole bunch of simple pieces. That's the idea. The connection is made by essentially putting dowels inside the voids that pass between the wall stem and the cap and filling that with concrete. Very simple, easy to design, because this joint being just below the beam seat essentially is a low moment demand connection. If you think about it, if we build bridges with stone masonry abutments that have just mortar between the stones, there's with a gravity section, there's virtually no force going across the joint. So it's a very easy connection to design. Here's a photo of a bridge built in Maine, Kittery, Maine, where the Maine DOT took these details and actually executed them very well. You can see where they got creative. The footing is shown on the right with dowel bars coming out of the footing in clusters. Those bars line up with the voids in the panel. Panel is set over the bars. The voids are filled with concrete up to about 3/4 of the height of the wall panel. And then they come back a day later and then put dowel bars in the upper portion of the panel. You can see that in the center photo. Then the caps are placed on top of that and filled with concrete to complete the abutment. Very simple construction, very fast construction. You can see the aesthetics of the abutment is beautiful. Very nice bridge. Another detail that I like was developed in Washington State, where essentially they built the bridge upside down. They constructed the column or the wall panel before they put the footing in. This is great for pile-supported foundations, and the idea is to have a precast column with a temporary support on it, and then you set that down, rebar cage is set around that, and you pour the footing. Even though it's cast-in-place construction, it's very fast construction. Probably 2 or 3 days to build a pier. Taking it to the next level, Washington State studied this detail with a research project funded by Federal Highway, coming up with the idea here is to have the column set into the footing, cast-in-place footing, but there are no reinforcing bars passing between the column and the footing. This is a true socket connection. And the best way to do, best analogy to this connection is a mortise and tenon joint in woodworking, where essentially one wood piece is inserted into a void in the other piece, and it gives you a very strong and durable connection. The nice thing about this is you can tie the rebar cage ahead of time and then set the column in. They're showing the column being installed on the right with the bottom mat of reinforcing in place, but the reality is you could have both mats of reinforcing in place before the column is set. Let's go through some graphics showing how this might work. This is a round column. The provisions in the specification allow you to use exposed aggregate as opposed to a formed corrugated end of the column. So you can use exposed aggregate. The reinforcing bars need to be developed in the footing. Without hooks, you may need to use headed bars to achieve this, so we're showing that. As far as the footing reinforcing goes, you essentially take the standard footing reinforcement you would use if it was cast in place and move some bars around. The red bars denote those bars that are shifted. The diagonal bars are added to enhance the connection as well. So this is showing a footing, a spread footing, a shallow foundation, but this works really well with pile-supported footings as well. So once the bars are set, you insert the column on a leveling pad, you true it up, and then fill the form with concrete. Very simple connection, easy to execute, and very cost-effective as well. Full-depth deck panels are very popular in the U.S., and PCI Northeast has developed, just recently revised their recommended guide details for these panels. And this concept has been developed in a few locations around the country where we typically run the panels transversely, and that's perfectly acceptable. But this concept came up of using longitudinal panels, and there's some really significant advantages to this. You'll note that the joints between the panels essentially are over the top flange of the girders below. So we're using the girder as an actual form to hold the material we're going to place in the joint, whether it be concrete or UHPC. And you'll notice, so then reality is the only forming that's really required in the field that's significant are these transverse joints that are located at certain intervals. The overhang panels, we have to use a more traditional panel with voids in it because we need You could run longitudinal panels up to the fascia beam and then cast and place the overhangs if you want, but just a nice simple detail. So let's look at an example of where this might have been done, and it is in downtown Boston, Commonwealth Avenue Bridge, a very large, very complex ABC project that was executed a few years ago. You can see the joints running down where the top flanges are. Another advantage to this is if you have steel girders, you can shoot your shear studs anywhere you need to put them. You don't have to worry about pockets. If you use a bulb T girder, the details on the left show you can actually use straight bars with bulb Ts if the flange is wide enough. If you have a narrow flange, hook bars with concrete or UHPC work very well. So very simple details, and it really does simplify the precast panels without having voids in the panels. Essentially, they're rectangles with bars projecting from the edges. Link slabs are really popular for ABC because we can do span by span construction and make the bridge we can make the bridge jointless, not continuous. That's the key. And really, the key to continuity is we really want to get rid of the joints that leak and cause damage. So we have provisions developed for link slabs based on work done by Kaner and Zia in 1998. I circled one provision on the bottom that's really important, is that the skew of the bridge can be neglected in the link slab design. This is because the research done in Michigan showed that as skew increases, the actual forces acting on the link slab decrease. And so it's very interesting that we could do that and ignore skew in link slab design, which is a very common question that we get. PCI Northeast has also developed a beam called a next beam, the Northeast Extreme T. It's a heavy-duty double T that's quite a bit more robust than, say, a parking garage double T. There are 3 different versions of the next beam in production, all using the same form, which is nice. The next F beam is in the top, where the top flange is a form, where it is used to support a stay-in-place form used to support an 8-inch reinforced deck. The next E beam has a top flange that is more heavily reinforced. It acts as the bottom mat of reinforcing in the deck, and then a 4.5-inch topping is placed, reinforced topping is placed to complete the deck. And next D on the base is a fully decked section where the top flange of the beam is the deck of the bridge. The next D is probably your best option for ABC, but all 3 of these are very fast construction because we're eliminating a significant amount of the formwork that's required for typical conventional construction. Here's a photo of a bridge in Massachusetts that our firm designed years ago. One of the earlier next beams in Massachusetts is a next F beam. We actually curved the bridge by varying the overhang of the fascia beam. So it's a very aesthetically pleasing bridge. We don't need to put a square bridge in a round curve. We can actually put some slight curvature into these sections, and they work very well, very cost effective. Lateral sliding is really popular in the U.S. Because it's quick, it's less expensive than SPMTs, it's actually faster than many SPMTs, and it's very versatile. If you have room to build a bridge alongside the existing bridge, I would highly recommend using lateral slide. The detail on the right is a detail developed originally in Utah, and it's a common detail that works well for any kind of slide system, whether the contractor is using rollers, slide bearings, jacks, cables. That detail works for everything, which is great because you can give the contractor options for which slide mechanism they want to use. You'll notice that tooth on the back of the semi-integral abutment that projects down below the bridge seat. The next detail will show how that's used. Essentially, we put a notch in the back of the abutment. This is to prevent water and moisture from getting into the bridge seat when the bridge is completed. So let's walk through the sequence. We slide the bridge over, in this case on temporary slide bearings. Once the bridge is in position, the bridge is jacked up. It's very easy to jack the bridge, placing jacks between these slide shoes. Jack the bridge up. We set the permanent bridge bearings underneath the slide shoes, fill the joint in the back with closed cell foam, and set the bridge down. And very simple, easy details, very durable detail, and it's cost effective as well. TRS IBS is a technology developed by Federal Highway that I love. It's a great ABC product because you can build abutments really very quickly. Basically, the best way to describe a GRS IBS abutment is that it's like an elastomeric bearing. And when the bridge expands and contracts in thermal movement, the entire abutment flexes with the superstructure. So there are no bearings on this bridge. There's no approach slab because it's a reinforced backfill that does not require approach slabs. You do not get settlement that you get with normal abutments. And the facing is simply either dry cast block or, in this case, the photo on the right, these wet cast block. It's a bridge in Connecticut we designed a few years ago. It's a beautiful looking bridge, super durable. There's no joints in the bridge and there's no bearings. So it's very cost effective structures. So if you have a grade crossing, A lot of people are nervous about using these for river crossings, but if you have a grade crossing, it's a great solution. Another detail that I've seen that I love is this concept of using a precast back wall that's bolted to the end of, say, a steel beam. This is a semi-integral detail. The back wall cantilevers out beyond the end of the abutment, similar to the lateral slide details I showed before. And the key thing about this is the precast, the back wall, actually you can use that to eliminate the end diaphragms because it actually is the end diaphragm for the bridge. So again, it's a very cost-effective detail. Again, I mentioned before, we don't have time to go over detailed construction specifications, but the document does include all these specs. Some of the important ones, the first bullet is fabrication and assembly planning. If you buy a bicycle for your child, you usually have to assemble it or partially assemble it, and there are instructions on how to do that. Well, if you're building a bridge with prefabricated elements, we think it's a good idea for the contractor to develop an assembly plan so they have a step-by-step process that develops how to assemble the structure properly, taking into account materials and schedules and things like that. So we have very detailed provisions that we recommend engineers use for their specifications. Quality control for precast concrete, we've enhanced what's in the AASHTO LRFD bridge construction specifications. Repair of elements is an important aspect. Moving elements, there's inevitably damage may occur. We need to know how to fix those and how to manage that. And lastly, material specifications for common ABC materials, high early strength concrete, ultra high performance concrete, and non-shrink grout. We have developed performance specifications for all three of these. A lot of this is based on work being done that has been done by Federal Highway. So in conclusion, we have a specification. ABC is here to stay. There's really no reason why one should shy away from an ABC project. This is a national specification that was published by AASHTO. It covers everything you need for design, including loads and load factors, element design, connection design, tolerances, dynamics, SPMT lateral slide systems, and full construction specifications. So you have all the tools you need. So tools are there. You can design and specify an ABC project now. So really, I encourage everyone to go out and build something fast, which is the purpose of ABC. So I thank you for your time today, and I look forward to answering any questions we might have after this presentation is completed.
All right, Mike, thank you so much. That's a great presentation. Even a pavement materials guy like me felt like I kind of understood what's going on. So that's awesome. We did get a question in the chat, which may be too detailed to answer in the few minutes we have left here. But if we use roughened precast columns and a socket connection, do we still check for punching shear in the footing? And if we do, how do we go about it? Can you address that?
Yeah, I can address that. Thank you very much. I appreciate the question. It's a good question. The research that led to that detail, they tried to fail the connection in punching shear. They actually had a hard time doing that because the capacity was so large. The reality is as long as you meet the provisions in the guide spec as far as the thickness of the footing being equal to at least 1.1 times the diameter of the column, it will not fail in punching shear. I guess in theory you could check a traditional cone failure, punching shear failure. You would do it just as if it was cast in place. You use the same provisions for that. But as far as the column, the corrugated column end punching through the footing, the research showed that as long as you meet the provisions in the spec, as far as roughening the surface, you're good to go. There are provisions in the spec as well to check interface shear between the column and the cast-in-place footing, which essentially is a punching shear failure as well. So there are provisions in there with recommendations for cohesion factors and friction factors using the AASHTO LRFD bridge design specification requirements. So the answer is yes, you do check punching shear, and we have provisions to cover that for you.
Well, and I guess you and I talked a little before all this started, and so this is probably not a question that can be answered in 90 seconds. But as far as ABC goes, how much does it cost? Can you address cost a little bit in such a brief time? I know.
Yeah, I can do it. I have a 90-second answer. I got a 10-minute answer too, so I'll give you the 90-second answer. There's a lot of factors that affect the cost of ABC. I get this question at every conference I speak at. And the reality is ABC does tend to cost more than conventional construction, primarily because, well, there's a number of factors. I'll go through some of them. The first question is, how fast is fast? If you build a bridge in a weekend, you're going to pay dearly for that weekend. Contractor has to pay overtime. You need a lot more equipment, a lot more manpower. It's more difficult to manage. Handling of precast. And we do cast in place construction. The actual concrete is only handled once. It goes from a batch plant to the forms. You're handling it once. In precast, you're doing a batch plant in the shop into the form, then you're lifting it out of the form. That's the second time you're handling it, and you stack it. Then you put it on a truck. That's the third time you handle it, and then you erect it. It's the fourth time you handle it. Every time you move a piece of concrete costs money, and that adds up. Complexity of details can affect cost dramatically. I showed some of my favorite details today that are cost effective, so that'll help to keep prices down. Things like incentive and disincentive clauses. When you attach a huge disincentive clause to a contract, that tends to increase the cost. All this adds up to risk to the contractor. Contractors bid risk. Higher risk equals higher dollars in the world of contracting. So we as engineers, need to look at ways of reducing risk, maybe relaxing the schedule a little bit, simple details, keep incentive and disincentive clauses reasonable, and all of that will tend to bring the cost of the project down.
Great. Well, thank you so much. Again, we appreciate it. A great presentation.
Thank you.
I see there was something in the chat about the pier cap and shear checking, but if you don't mind, if you could address that in the discussion, so we can move on to the next one. But again, thank you so much for being here.
Thank you. I appreciate the opportunity. Good day.
Okay, well, looks like we're right on schedule here. Our next presentation is going to talk about bonded concrete intersection experience in Georgia and South Carolina. And I hardly need my written introduction here, because our speaker, Melissa Campbell, is both a dear personal friend as well as someone I worked with at SCDOT at the Office of Materials and Research for a good 20 years, I think, and so I'm delighted to continue to get to work with her in retirement. But Melissa Campbell is the Georgia Pavement Applications Director for the Southeast Cement Promotion Association. She previously served as the SCDOT State Materials Engineer and as a pavement design engineer, retiring in 2013 after 25 years. She graduated from the University of South Carolina with a Bachelor's of Science and a Master's of Engineering in Civil Engineering. So with that, we'll move on into Melissa's presentation.
Good morning. Thank you for the kind introduction, Andy. Today we're going to talk about Georgia and South Carolina's experiences with bonded concrete intersections. There have been a number of projects, and we'll be going over each of those. So why would we want to overlay a pavement with concrete? Well, concrete is a longer lasting pavement solution. I think most people know that, and that it can last 30 or more years with minimal maintenance. Concrete can also be the cheaper solution when long-term maintenance and user costs are calculated in. We like to say that you can get in, get out, and stay out, and we'll talk about some examples later where we've been able to do that. So what are the concrete options that are available to us? You can either do an unbonded overlay, where you remove 5 to 12 inches of existing pavement and replace with concrete. This allows you to maintain curb grades and work with the existing cross section, not have to make any changes to earthwork. Or you can remove no asphalt, or up to 5 inches of the existing asphalt, and overlay with concrete, and that would be a bonded overlay. So what's the distinction between the two options? An unbonded overlay with concrete is designed in a similar manner to a traditional pavement. It may depend on the material underneath for support, but it does not depend on being bonded. Now, being bonded will make it stronger if that bond is achieved during construction. So it's not a bad thing if it bonds, but it is not a requirement. With concrete pavements are rigid. So they act more as a beam, so that the vehicle loads are distributed over large areas. And so in this example, in this drawing, with an 8-inch slab, you have a 100 psi tire pressure. That's what tractor trailers run. And that pressure will be distributed over an area of somewhere between 15 and 20 feet, maybe even a little bit more than that. And so that loading goes down through that slab, and it results in subgrade pressures of between 3 and 7 psi. And that's going to cause very minor deflections. And of course, those are very low subgrade pressures. Now here, the subgrade uniformity is more important than the strength because you don't want it to be much weaker in some areas than others. Now, asphalt pavement design principles, asphalt pavements are flexible. They're going to follow what's underneath. And so the distribution of the loads depends largely on the pavement thickness. So here we have a 10 to 14 inch pavement, and that load, that same 100 psi load, you can see it's contacting the pavement, and it goes down at about a 45-degree angle. And that results in a depression basin of about 2 to 3 times the thickness of the pavement. So here we're going to be somewhere between 30 and 42 inches, whereas before we were 15 to 20 feet. That's going to cause that contact pressure on the subgrade to be much higher. It can exceed 20 psi. And so it's much higher and much more concentrated. And the deflections are going to be higher. And here, your subgrade strength or stiffness is very important, because otherwise, if it's not strong enough, it's going to cause depressions in the new pavement. So if you're doing a thin bonded overlay, what are the design principles that guide us there? So if you have asphalt surfaces unable to resist traffic braking or accelerating forces, especially at intersections, this is usually where this is going to happen, of course, then that's when you can go to a hybrid structure that will be sufficient to carry the traffic loads. Maintaining that bond is crucial to keep the two layers acting as a single unit. It has to act monolithically. It's just like when you're doing multiple lifts of an asphalt pavement. You have to bond them. And so in this case, if the bond is lost, the stresses in that concrete layer will increase greatly, and that's not desirable, of course. So we're going to look here at bonded versus unbonded behavior. On the left, in the bonded behavior, we have a bond between those two layers. And so if you notice, the tension at the bottom of the concrete layer is very small. And that neutral axis, where it changes over from tension to compression, is low in that layer. And that's a good thing, because concrete, of course, is good in compression and not quite as good in tension. And so then the tension increases down through the asphalt layer. But even there, it stays reasonably low. Well, whereas on the right, if you have an unbonded overlay, that neutral axis is pushed up above the midpoint of that layer, and that tension increases greatly. And the tension in the bottom of the concrete layer is even greater than the tension in the bottom of the asphalt layer. And so this is when you're going to experience cracking. So what are some suitable candidates for bonded overlays? What are we going to look for? Like we talked about, we need stable support conditions. If you have localized weak areas, you can strengthen those. That's probably going to happen when you have an intersection that has been widened or had turn lanes added or multiple iterations of that. If you have surface distresses, if you've got rutting and shoving of the surface layer, but not deep in the pavement, and this is where you're going to have to do some investigation to discover where the rutting is coming from. If there are deep ruts present, then you need to find out if that's in your asphalt layers or in your subgrade. And if you have top-down cracking, this is mostly age-related, and so it's not an issue deeper in the pavement. You need a minimum of 3 inches of asphalt remaining after you do the milling, because otherwise you won't have enough to work monolithically with that bonded layer. Now, what are some poor candidates for a bonded overlay? If you have significant structural deterioration, if you've got high-severity fatigue cracking, rutting of the base and subgrade, these are not good candidates. That pavement has already reached its useful life, and this would be a good candidate for a thicker, full-depth replacement with concrete, or even if you did leave some of the asphalt behind, it would be an unbonded overlay, because no strength would be contributed by that underneath layer. If you have stripping of the asphalt layers, there again, that's going to cause those layers not to act monolithically. So if the stone in those layers has had the asphalt stripped off of it by water intrusion, then that's going to be an issue. Or if you have poor drainage, that's something that needs to be addressed before you do any kind of overlay. and especially if you have inadequate or uneven support. You need to know what's going on underneath the pavement. And if you have inadequate base structure, you're not going to want to put something else on top of it. You really just can't bridge with a bonded overlay. You need a good support structure. So how do we decide how thick to make our bonded overlay? Well, there are several methods available. There's a website called pavementdesigner.org, and that has options for designing a bonded overlay. There's also a bonded concrete on asphalt mechanistic empirical method that was developed by the University of Pittsburgh under a pooled funds study. Both of these options are free. They're web driven. You can just search, you can go right to pavementdesigner.org or search for BCOA concrete asphalt, and it will lead you to the University of Pittsburgh version. And like I say, they're free to use. They have a lot of background information and documentation. This is what the interface looks like for the BCOA ME method. And here are the states that contributed to the cost of this pooled fund study, and I want to express my appreciation for their financial support and their technical support as this process was developed. But if you need any help with designing these, Andy Johnson and myself are glad to help you. Just contact us and we will be more than happy to guide you through some of these. Okay, so what about joint layout? We've got our thickness determined. So where do we need to put joints, or where should we avoid putting joints? Well, anytime you're building pavements, you really want to avoid placing longitudinal joints in the wheel path. And this is more joints from adjacent pools than it is saw cut joints. But if you can avoid saw cut joints in the wheel path, that's better also. Sometimes using a smaller slab size, less than 6 feet by 6 feet, can reduce your overlay thickness, but you need to balance that reduction in thickness for the need to increase your joint sawing, because if you go thinner than 6 inches, then you're probably going to need to go down to, say, if it's a 4-inch overlay, you're probably going to need to use 4 foot by 4 foot panels, and so you need to look at those costs and balance that. Okay, what about material considerations? What do we need to think about here? Well, the type of concrete that gets used fairly often in these is a high early strength concrete, because this is going to allow you to open it back up to traffic a little bit sooner. So you need to think about that, and also consider using fibers in the concrete when the overlay thickness is 4 inches or less. These fibers will help hold the panels together better than not using fibers. And then the fiber type and the quantity should be selected so that you have a minimum residual strength of 20%. Now, some other construction considerations. The milled surface is a good surface to bond to, especially if you're doing thinner overlays, 4 inches or less. Surface planing is not a good idea, and even if you're going to overlay on top of existing asphalt and not remove any, it's still a good idea to run a milling machine over it to roughen it up so that you have a better bond between the two layers. So the milling depth should remove all the surface distortions that are greater than 2 inches deep. You want to match your curb or adjacent structure elevations, not just for ride, but also for ADA accessibility. You've got to take care of changes in your cross slope, but you've got to be careful not to mill too much. That's a fatal mistake. It can cause some issues. We've had those problems in South Carolina. Other construction considerations, after the milling, you've got to make sure your surface is clean, because you can't bond to a dirty surface. So it has to be swept thoroughly, all the dust has to be removed with compressed air, and the surface needs to be damp before the concrete is placed. Not wet, no standing water, but mist it with water. That will reduce your surface temperature and also reduce the moisture absorption from the concrete. This project was run using a pilot car, and as you can see, they were able to maintain traffic as they were placing this bonded overlay. If you have driveways or roadways that intersect your project, you can build small ramps out of millings, or you can leave a section out to come back and do it maybe an overnight closure. This appears to be an entrance into a business, and so you could work with the business to do that section while the business was closed, so that you wouldn't interrupt their workers coming to and from. Okay, some examples. This is one that we did in South Carolina back in 2000. We did the construction in 2005. We started the planning in 2004. Conway is just northwest of Myrtle Beach, and the two main routes to get to Myrtle Beach from the middle of the state, and even from people who are coming from far away, are either 378 or US 501. Well, this was the intersection of US 501 and 378. And so it got lots and lots of traffic. And even for trucks, this was the way they got into and out of the Myrtle Beach area. So you can imagine it's very, very busy. Well, the district had contacted us in the pavement design office because they had extremely severe rutting. And they had about 15 inches of asphalt pavement, and so it theoretically should have been fairly stable. But they were having to go out there every 3 or 4 years and mill off asphalt and replace it with more asphalt. They had tried several different times. Well, when we did the coring to locate the layer that was rutting, to make sure it wasn't rutting in the subgrade especially, it revealed that there was a sand asphalt layer that was about 10 inches down that was the source of the instability. Our experience with sand asphalt is that sometimes it's very stable and other times it is not stable at all. And this was one that, as you can see, it was 10 inches into the 15 and it was very unstable, so it had to come out. So we started thinking about what we could do. Well, we decided to mill 10 to 14 inches because we had to get that much out to restore the cross slope. It was so bad that people that were turning left into a fast food restaurant were high centering their cars on the humps. And so something had to be done. So we decided we're just going to mill that out and then make sure we were 10 inches deep at the curb, put a 10-inch thick overlay of plain jointed concrete pavement with 1.5-inch dowels and 15-foot joint spacings. And this is a typical pavement arrangement for us. So this was before the project was done. This was in 2004 when we were planning. And as you can see, these ruts are pretty severe. The resident construction engineer and his assistant spent a lot of time going around to the businesses, talking to them about what was coming, and contacting residences about the detours. And we tightened down pretty hard on this. We gave them 2 weeks to do the concrete paving. They did it in February, which was the lowest traffic season. They had to maintain traffic in one direction, and they could have a 24-hour closure from Sunday at 8 p.m. to Friday at 6 a.m. Anytime in there they could be closed for 24 hours at a time. But then they couldn't be closed, of course, on the weekends. It was tight. Well, this is an overhead shot of the project, and the vertical leg, this was 501, and then 378 comes in from the left here. And you can see after the concrete, and this was during the project, but you can see there was traffic moving. No, this is after the project because the concrete runs pretty far out on the 378 leg and not very far out on the, on the 501 leg, but not very far out on the 378 leg. But this was a huge project for us because there wasn't really a way to get people to the beach otherwise. So this is during construction where they've milled it out, and as you can see, there are a good many businesses, but some of these just shut down for the 2 weeks. They just closed up business and went home because they knew that this had to be done. They were tired of the constant disruption every 3 or 4 years. So here's where we were pouring the pavement, placing it. Everything went really well. We had cooperation with the residences and all the contractors, and this is 10 years after the project was completed, and we've had no issues out there. It's now been 16 years since it was completed, and so that's at least 4 cycles of work that would have had to have been completed on this intersection. They've had to do nothing, and so the district was very well pleased, and the public was pleased too, especially people that lived in this area. Another photograph of it. It was a really good job. It worked out extremely well. This is another project that we did in Lawrence County. It was a 14-mile section of I-385. It had been built as a U.S. highway, and we needed to upgrade it to interstate standards. And so we did a huge project here. We did an unbonded overlay here, but we went in and milled 6 inches of the existing asphalt, maybe more or less in some places depending on the horizontal and vertical curves, and especially under the bridges. And we replaced it again with 10 inches jointed plain Portland cement concrete, and then did RCC, roller compacted concrete, on the shoulders. We started on January the 2nd of 2010, and they did the ribbon cutting on July the 23rd, 2010. We had one direction of the interstate closed for the entire length of the project, and then had to detour people. Anybody that was trying to go north had to be detoured. But it really went extremely smooth, even though we had a lot of bad weather that winter. But it was a really good project. And this one has served us well. This is a Google map photo, so it's not real, but it has really been a good project. We've got a good many intersections around Georgia. This one is in Waycross, Georgia. This is District 5, which is kind of below Savannah, or Savannah and below, and along the coast, and then some inland. And there are lots and lots of intersections that have been placed because they had such bad rutting and shoving. And some of these have had a little bit of cracking in some of the panels, but they're still serviceable. This one, it was wet that day, but as you can see, it's had traffic signal loops cut into it, but it's still working. No issues. Garden City is up near Savannah, so it gets a lot of port traffic, a lot of truck traffic. This one looks good until you get to this slide, but I'm fairly sure that this is where that road had been widened or a turn lane added, and we didn't have sufficient thickness of asphalt when this overlay was placed. But overall, this one has served well. This one is in downtown Columbia, and it has been in place for, I think, about 18 years now, and it has served us very well. There are some cracked panels, but not badly so. These are it's actually holding up extremely well. This one got covered up with asphalt during a beautification project, and as you can see, the asphalt that they put on top of it has begun to rut. We didn't know they were going to do this, or we would have tried to work with them, but they wanted to make it all look uniform, and so that was the decision they made, and this is what we've ended up with. This one's in Toombs County in Georgia. Most of these, this one's in Appling County, and as you can see, most of these are pretty major intersections in towns. That one has some cracked panels, and some spalling. So those panels probably need to be replaced, but it's not like they've caused huge issues. Another one back down in Ware County in town of Waycross, Pierce County, and some of these are small communities, but this was the one that I found really interesting because this is a very rural area, and Georgia is kind of split. People say that there's two Georgias. There's Atlanta and there's the rest of Georgia, and this is pretty far south in the state, but it is a really heavily agricultural area. And so Georgia grows lots of cotton, lots of peanuts, lots of peaches. Timber farming is huge. Soybeans. They're the blueberry capital of the United States. There's lots of products that are produced here. And I was at this intersection, and this is out in the middle of nowhere. There's not even a store on any of these corners. In this picture on the right, to the right, there's a parking lot and an old store, but I think it's being used as a residence now. But while I was there, I was probably there for 4 or 5 minutes to 10 minutes, something like that. I saw 2 fully loaded cotton trucks, 2 fully loaded peanut trucks, and a half of a manufactured home or a mobile modular home being towed through this intersection. So this intersection gets a lot of traffic, and so this was a really good choice for them because now they don't have to worry about the pavement failing on them all the time. And so it really is a benefit to the entire community. Okay, so for detailed information, the CP Tech Center, the National Concrete Pavement Technology Center, has a publication that outlines how to use concrete overlays. And this is a big topic nationwide. People are using overlays more and more, and so we are more than glad to help. If this publication is available online, but we can also provide you a hard copy with it, a hard copy of it if you contact us, if you'd rather have a hard copy. And also we're available to assist for anything that you need as you start thinking about doing overlays. We'll visit the site, help you with design, whatever needs to be done. And this is a cartoon that a coworker of mine included as we get to the question part, that these are some of the answers you might get. You might just get an enigmatic smile, or an insult, or a joke. Never know. But we are glad to at least try to help you. And my favorite thing to say is that I don't know but I can find out is a good answer to a question. So any questions that have been submitted through the chat function during this presentation, of course, we will try to answer in the 5 minutes that'll be remaining. But if we don't get to those questions during that question and answer period, we'll contact you afterwards and make sure that you have the help that you need. So please reach out to us. This is my contact information. You can also reach any of us on the SCPA staff by going to the Southeast Cement Promotion Association website and clicking on the Meet Our Staff button, and everybody's contact information is there, and we are all here to help you. That's what we get paid to do, and we're more than glad to help you, and we all are passionate about what we do, and we would look forward to being of assistance to you. Thank you for your attention today, and I'll move into any questions. Thank you so much.
Well, thanks, Melissa. We appreciate that. I know being a lot of those projects were in South Carolina, so both you and I spent a lot of time messing with those things. We did a bunch of thin bonded overlays. They used to call them ultra thin white toppings back in the old days, and we had a lot of them that didn't work great, as it turns out. And the ones that didn't work great, when we went out and took cores, what we found was we had milled through, trying to get all the grades nice again. We had milled through most of the asphalt, and so when you are looking at 3 inches of concrete over 2 inches of asphalt, that's not a great recipe for success. But I will say that the ones that had the appropriate thickness, now I want to say it was 2001 when we did those things, 2001. Those are still out there chugging away. Like you showed the one on Blossom Street, and the one, it was a slight misstatement on the other one on Hardin Street in
Hardin
Columbia.
Street, yep.
Yeah, Hardin Street at Gervais, they actually removed the ultra thin, or the thin bonded overlay, as part of an intersection beautification project over my objections, and sure enough, it has rutted just as badly as it was before we installed it. So there's a before and after for you. So I always have a little bit of schadenfreude every time I drive through that intersection. It's only a few miles from my house. So,
yeah, and sadly, one of the sections that did not work for us was over in Casey, which is a suburb of Columbia, and it was on our boss's commute route to work. And so, if he came in a bad mood, you had to kind of hide.
Oh yeah, I would get daily updates on how that one was going, because that was one of the ones that we milled off too much asphalt. And so yeah, I learned the valuable lesson as a young engineer, or maybe not so young at that point, but still, don't ever put experimental sections on your boss's commute into the office. So but the one on the other side of the intersection is working pretty well. But yes, that was something. But Melissa, you've been dealing with the folks in Georgia some. What's their thinking when they do these intersections? What's what are they aiming for when they do that?
They're aiming for long life. They've experienced the same things that we have with intersections like the one at 501 and 378 and over in Conway, is that if you have an intersection that starts to rut very often, even if you mill several inches of asphalt and replace it, it's going to rut and shove again. And they use a lot of four-way stop intersections, just like we do here, and most states do. And those especially are problematic because every truck has to stop and start again. And so that's what they've used it for. They really started using it around the port in Savannah, because once the port got busier and busier, they started experiencing rutting and shoving. And so they just started there. And now that's just their, if they have an intersection that ruts and shoves in the asphalt, they just go out and they have maintenance contracts that they issue on a yearly basis to have things like this done. And so they just get one of those on-call contractors to come in and replace the asphalt, at least the top few inches, with concrete, and then they go on about their business, and then they can go fix another one and not have to keep coming back every 3 to 5 years. So that's their main purpose. And for them, it's, especially in that district, it's just the solution. That's just what they use.
Yeah, my recollection is that they started doing these thin bonded overlays a little later than we did in South Carolina, about 2005. But I think they unlike us had some really good initial results, and so they've kept up with it, and so I'm always pleasantly surprised if I happen to be driving around South Georgia to just randomly come up on one of these intersections. So they're doing a lot of them. So VDOT, if you're interested,
Oh yeah,
call me, call Melissa. We're happy to talk about it at probably greater length than you're willing to listen. And so on that note,
oh
thank
yes.
you, Melissa. There is one question that popped in actually on the chat. I feel like I should answer. The bonded BCOA software will tell you the. Sorry, I'm answering your question for you, Melissa, because like I say, I love this
That's
stuff.
fine.
But normally they're 3 to 6 feet. It kind of depends on the situation, and so these are really almost like cast in place pavers than they are a concrete pavement with a beam type situation. So on that, I would need to move on, but I'll be happy to answer, or I'm sure you will be happy to answer. Sorry, I'm stealing all your thunder, Melissa, but we'll be happy to answer the questions online. And so again, thank you for doing this. All right,
So
now it's
welcome.
time to move on to our final presentation of the day by, other than the closing remarks from Andy Babish, but our next presenter is Sam Tyson with the FHWA, and he is also going to talk some about bonded and unbonded concrete overlays, but it's part of the Everyday Counts initiative, and so this is his topic today. But Sam is a concrete pavement engineer in FHWA's Office of Infrastructure located in Washington, D.C. He's a registered professional engineer in D.C. and a graduate of the University of Virginia, where he earned both a Bachelor's of Engineering and a Master of Science in Civil Engineering. Sam served on active duty. I should have read this more carefully. Sam has also served on active duty, and so on that note, I'm going to I guess, turn it over to his presentation, and then we'll come back afterwards and talk a little.
Hi, I'm Sam Tyson with the Federal Highway Administration in Washington, D.C. I'm going to be talking about concrete overlays, and in particular, I'll be referring to the concrete overlays that are a part of the Federal Highway Administration's Everyday Counts program. FHWA's Everyday Counts program includes both asphalt and concrete overlays. I'll be talking only about concrete overlays. Of the 7 technical areas to be included in the Everyday Counts program for 2021 through 2023. In this slide, I've indicated where you can use concrete overlays, and basically, as you look down the list, they can be used anywhere in every kind of situation. And it's important to note that all of these things are done in an effective, cost-effective, and sustainable manner. Here is a list of readily available documents and website sources for information for planning and executing a concrete overlay project. but there are many more references available as well. One very important part of planning any overlay project is the maintenance of traffic. During the Everyday Counts program, FHWA is offering the states financial incentives to participate in the use of these technologies. Basically, concrete overlays come in a variety of configurations, which include bonded and unbonded concrete over asphalt, bonded and unbonded concrete over composite pavements, and bonded and unbonded concrete over concrete pavements. Here is an example of an unbonded concrete overlay on a composite pavement in Iowa, both the paving operation on the left and the completed pavement on the right. Here is an example of an unbonded concrete overlay on concrete pavement in Illinois, and it's important for an unbonded overlay on concrete to be assured that there is little bond between the concrete overlay and the underlying concrete pavement. So this is accomplished by either the application of 1 inch to 1.5 inches or 2 inches of asphalt over the existing pavement before the overlay is applied, or in this particular case, the application of a geotextile material. Here is an example of a bonded concrete on asphalt existing pavement in Oklahoma, and you'll notice on the left that that particular photograph shows the surface condition of the existing asphalt pavement after milling, and that milling operation provides assurance that there will be good bond between the concrete overlay and the existing or underlying asphalt pavement. Here is an example of a bonded concrete on composite pavement in Iowa. It's being done one lane and a shoulder at a time. And you'll notice that maintenance of traffic is an important part of this project. You can see the traffic being led slowly in the opposite lane for safety purposes, obviously. And the completed pavement is open to traffic in the photo on the right. Bonded concrete overlays on existing concrete pavement can be relatively thin. And you can see here a 3.5 inch concrete overlay being applied on an interstate pavement in Kansas. The Colorado DOT has developed and utilized the 6x6 by 6 inch concrete overlays on asphalt pavements for a number of years, and they've placed more than 1.5 million square yards of this type of concrete overlay on asphalt pavements. The western part of the United States is not up to date. In particular, California has a number of concrete overlay projects, but it's not been updated at the time that this particular photo was taken of the website. If there are any questions, I'll be happy to address them now, or if we have time, or later. I'll be available after the conference is over. So I look forward to talking to you. Thanks. Bye-bye.
All right. Well, thank you, Sam. Are you there on in the interwebs out there somewhere? There you are. Oh, I think you're still muted.
All right, I think I'm
There
all right. Good. Well, I think I would yield my time to Melissa, or even to you. She gave a great presentation and covered just about everything I think that I would like to have covered. I would comment that we have a cooperative agreement with the CP Tech Center in Iowa, and we are, in fact, very close to publishing an updated volume of the guide to concrete overlays. She showed the picture of the third edition, which is available now. So the fourth edition will be available very soon. I'm glad that she mentioned, and I think you also mentioned, retaining a minimum of 3 inches of asphalt when a pavement is milled. That's a very important aspect of concrete overlays on asphalt, is to leave enough asphalt that you've got a sound base to apply the overlay to. So I'm real happy that you and she both mentioned that. Perhaps the only thing that Melissa didn't mention, and I may have missed it, I apologize if I have, is the use of the interlayer for the application of concrete overlay on concrete, because there it's extremely important to not have a bond because of reflection cracking. So the use of 1.5 inches to 2 inches of asphalt or a geotextile interlayer is important in that case. I think she did mention that there is some bond, even when we talk about unbonded concrete on asphalt, there is some bond, even in a case where the pavement is not milled, or it's very smooth, or it's been in place for many years. It's highly oxidized, but that would be considered an unbonded application. However, there is some bond, and in that case, that a little bit of additional bond is actually a plus, because it increases the load carrying capacity of that pavement. I think those are the only points that I would make. I don't see any particular questions, but
I guess one thing sorry, I was looking at the YouTube feed rather than you, and I'm like, oh, he's still talking, but you're about 10 seconds behind. So hope I'm not putting you on the spot, but I'm always confused about these different pots of money and the everyday counts thing. You mentioned the stick, and my wife is still an engineer at SCDOT, and she's used stick money for some other stuff, and she was trying to explain it to me, and I still never quite got it. But what sort of support, if for a state that wants to do this, what sort of support is out there if they do want to try this someplace?
Well, my understanding is that the stick committees, each state, of course, has a committee or a group of people that make up the stick. They decide what kind of projects they would like to, in this case, apply for federal funding from FHWA. It's my understanding that we are, as I indicated in one particular slide, offering up to $100,000 for the use of this technology. I'm not sure about the additional funding. It was not available as of a week or two ago, the $1 million for a project that suggests a longer term commitment to each of these particular technologies. So the award from Federal Highway could be as low as $100,000 or as high as $1 million is my understanding. It takes a little bit of time for the funding to become available, and that's why I'm not absolutely sure right now, but that is the intended level of funding. Yeah.
Yeah, and there's a question on the chat here that says, when do states have to state their intentions to use ED6 TOPS program to advance their concrete overlay technology? Is there a deadline? And that's my problem. I can't keep up with all the acronyms, but whatever the TOPS program is.
And I'm a little bit in the same boat, because my understanding was that the deadline was the first week of April, and now it seems to have been extended into May. And the reason I say that is because I was invited to speak at a meeting of the stick in Pennsylvania next week, and I just got a notice that they've delayed it by about a month which would be beyond what I thought was the initial deadline for the application for funds. So I'm really not sure. It's something that may be somewhat fluid at this point for reasons that I can't explain, but it looks like it is later than April. It probably is going to be sometime in May or perhaps June. I really don't know.
Okay. Well, I guess the other thing from the FHWA perspective, do you have any thoughts about when an overlay, bonded or unbonded, might be a better choice than perhaps or maybe I should say, when do you bond and when do you not bond?
Well, again, the choice of concrete over asphalt, I think Melissa really focused pretty heavily on the use of concrete in intersections, just because of the rutting and shoving effect of traffic. We know from experience that asphalt is going to be replaced periodically. It might serve very well for 5 or 6 years, but concrete probably would be more in the 20-year range. So it does make sense in terms of traffic management to and cost as well to use concrete in that case. As far as selecting a bonded versus unbonded overlay, typically a bonded overlay would be applied, first of all, in a pavement where you really are looking just to increase load carrying capacity because of increase in truck traffic and so forth. But you would also only use a bonded overlay on a pavement that it's in pretty good shape. It requires a relatively small amount of repair, rehabilitation before the overlay is applied. Now, it could be in places a full depth repair. That's not the issue. It's the overall condition of the surface of the pavement. If you have pavement that has, for example, in concrete, an inch and a half, not an inch and a half, but a half inch of faulting at each joint, mid-panel cracking, some minor spalling, or even large amounts of spalling, that is a good candidate perhaps for an unbonded overlay, because you're going to prevent those defects from reflecting through the new concrete by applying that inch and a half to 2 inches of asphalt or a geotextile material. So, I mean, I hope that somewhat answers your question.
Mm-hmm. No, that's good. That's good. And we have another question on the chat here from Muhammad El Fino, and he was asking about a material called tin drain. I don't know if are you familiar with that? It's a high stiffness core, he says here, between two non-woven geotextiles. Have you had any experience with that?
Actually, I have not, and I'm glad Mohammed is on the feed today. He retired from Virginia some years ago, and I don't know whether he's back in Egypt or in the U.S.
Jacksonville.
But, okay, I would say hello to Mohammed. I'm afraid I'm not familiar with that material. No.
You know, I believe I looked at that, as I recall, or I looked at a material. I do recall that it was made in Italy, and I think the only problem with tin drain, while it's a great great technical concept, was that the price was prohibitively high. And so I think you can achieve a lot of the similar results with these geosynthetic interlayers that are designed for that purpose, and those can be used for drainage and separation. And they run, my understanding is installed, they run about $2 a square yard, but don't take that to the bank for sure.
Yeah.
That's just my impression.
I'm guessing that it probably has very good drainage characteristics, that maybe that's something that they've incorporated, but I'm not really familiar with it. I don't know.
as I recall, it was sort of a channel between two stiff plastic channel between two geotextile layers, and so it was meant to serve that purpose. But you'd really want to have
It
a
sounds like
lot of
that's,
drainage.
yeah,
It may be almost more than one would need under normal circumstances. And
right,
so
right.
anyway, enough about that. Again, Sam, appreciate your time and your effort putting it together. It looks like you might look like another question popped up in the comment here. I guess Greg Dean, who has dealt a lot with airfield pavements, notes that 7 airports have completed overlays, but FAA only permits unbonded and thus 5+ inches for general aviation. So just another tidbit out there if you're in the airport field.
Oh, that's
And
interesting. Yeah.
so anyway, once again, Sam, I do appreciate it. And I guess, obviously for any of you out there in internet land, if you have any more questions for Sam, please feel free to post them in the comment. And I guess with that, maybe we'll move on to our next presentation. So thank you very much.
Well,
Sam.
if I could, I'd like to end by once again thanking
Oh, yes.
Melissa for an excellent presentation. So that was very good.
So, well, thank you. I appreciate it. And so, okay. So I guess we'll move on to our final speaker of the day, and this will be the last you hear from me. Because after Andy Babish speaks, Roger Faulkner is going to come on, and he's going to do the drawing for the prizes. We obviously can't do the M&M stuff and all the other stuff that we normally do in person, but we are giving away a $100 gift certificate of some sort, and so Roger will be will be doing that part just like he does in Richmond. So with that, I guess our closing remarks today come from Andy Babish of Virginia DOT in the Materials Division. And Andy is a PE, and he obtained his bachelor's degree in civil engineering technology from Bluefield State College and his master's of science in civil engineering from Virginia Tech. He's been with VDOT for 23 years, with the last 13 years as state materials engineer. So I guess without further ado, I will turn it over to Andy for his closing thoughts. Andy?
All right. Good morning, Andy, and thank you for the opportunity to just say a few things to the audience this morning. First of all, I want to thank the Planning Committee and congratulate them on a successful conference, virtual conference. This pandemic kind of threw a wrench in our normal mode of operation, and but as the commissioner said yesterday, we are a resilient workforce in the transportation industry, and that goes for our industry partners and VDOT staff alike. The COVID pandemic challenged us all. It still has challenges. We still face challenges with it, but it's challenged us in our personal lives as well as in the workplace. But certainly in the workplace, we have met those challenges. And just this conference, having to switch to a virtual mode, is a testament to the resiliency and the partnership and the cooperation that we have with industry partners to still try to deliver successfully, whether it's information or projects that were certainly showcased yesterday and today. Some great projects and great information that was put out there. And I hope the audience can take some of that back and explore it and use it in their operations and take advantage and find it beneficial. The presentations, I know somebody had asked earlier, or I saw in a chat, I just want to point out, Andy, that the presentations will be posted on the VDOT Materials Division's webpage for those that are interested in going back or downloading them or looking at them and making further notes and contacting those speakers. Those presentations will be available probably sometime next week or so on our website. So go back and look at those and visit that, and you can get that information as well. So with that being said, Andy, I just want to thank you again. I want to thank the planning committee for all of the hard work they did to put on this virtual conference. This was a different animal, and I know all of the speakers, really appreciate them, doing their recorded presentations. That was something very different for a lot of people. But by all measures, from the seat I sit in, this has been a great conference. And you guys did a really, really good job. And I just want to say thank you. And let's hope next year we're able to meet in person and sit down at the table and talk, as opposed to looking at each other through a computer camera. So with that being said, thank you again. Roger, I know you want to give away a gift card or some money to some folks. So I'm going to get out of your way and wish everybody a great week and a great upcoming weekend. So thank you.
Thank you, Andy. Always appreciate you giving your closing remarks. And before we wrap up, I would like to just put a big shout out there to the entire planning committee and all of our speakers. I think this year proved to be, in light of it being virtual, I thought it came off as at the same level of technical quality we've always been used to seeing. For those who've been to the conference, in the past, typically I end and come out with something that looks a little bit less than normal attire, but for today, I hate to disappoint you. I just didn't think I could pull that off as effectively behind a screen. So with that being said, like we did yesterday, how we're doing this, we're pulling up our list. If you're not aware, our total number of registrants for this conference was 680, an all-time record. And from that list, we basically pull it up, and we're going to do a random number generator and from that list, and we'll see who the lucky winner is today. With that, let me pull this up. Click. And today's door prize winner is Billy Jenkins of Moffett and Nickel. Congratulations. We'll be sending out you an email with the details on your gift certificate. Yesterday's winner was Jewel Stone with the Georgia Department of Transportation. Congratulations to both of you. Thank you for joining our 20th Virginia Concrete Conference. We kindly ask you, after today, you will be receiving an email with an evaluation form. We'd kindly ask you to take a few minutes to complete that. Your feedback's very helpful for us as we begin planning later this year for next year's conference. And also, as Andy mentioned, the presentations will be posted on the website, and Mary Lynn will send you another email letting you know when that is ready. Enjoy the rest of your day and have a great weekend. The Virginia Concrete Conference is officially adjourned. Thank you all.